Okay, we looked at the Zeeman effect last week. We said that if you take the atom, put it in a magnetic field, then if there is an electric dipole moment, there will be an additional potential energy due to this magnetic field, in addition to already existing potential energy, if any. And then we said that the electron, if we semi-classically imagine it as going around a circular trajectory, it will have a magnetic dipole moment given by E over m2m h bar times the angular momentum. No, there's no h bar. This will be the magnetic dipole moment, so it will have a potential energy, an additional potential energy given by E over 2mb h bar times delta times mz, where we had chosen the z-axis to be along the magnetic field. So essentially this gave us a splitting between in the energy values. Before, in the absence of the magnetic field, the energy depended only on the principal quantum number. And now if we have a magnetic field, furthermore, now the energy depends on mz value. Or ml, sorry. And the observable consequence of this was the transitions, the energy of the transition, the changes in the differences in the energy values, which was essentially determined the frequency of the photon emitted. It's now that the change in E1 over n squared. Let's say this is, let me ignore that one. The frequency in the absence of the magnetic field plus a contribution from the magnetic field. EH bar over 2mb delta ml. And delta ml could only take the values 0 or plus or minus 1. So before, in the absence of a magnetic field, we saw a one line. Now in the presence of the magnetic field, that line basically splits into 3. So we should have 3 nearly spaced lines in the spectrum. Well, when is this relevant? Well, if you, for an example, if you think the light coming from the sun, there will be absorption spectrums. Well, the sun has a magnetic field, not a small one. So the spectral line, the absorption lines in the spectrum of sunlight should be split into 3. And that is what we observe. That observation couldn't be explained in the Bohr's model, but now with this quantum mechanics, we could explain that. And this is what's called the Zeeman effect. And then we said that, okay, if there is a magnetic field, you see, this is what happens if you have a uniform magnetic field. If you have a non-uniform magnetic field, then there's a force acting on our magnetic dipole given by the gradient of mu dot b. You see, if B is non-uniform, this will be non-zero. If B is uniform, this is 0. Mu is constant, B is 0, B is constant, so it would be 0. But in the presence of a non-uniform magnetic field, there will be a force. So then we said that let's imagine we have a region of space which has a non-uniform magnetic field. For example, this is one means of creating a non-uniform magnetic field. You get two magnets. Let's say this is the North Pole, this is the South Pole. We have the North Pole, we have the South Pole, and then let's say you just send some atoms there. Let's say that the electron in these atoms are in some L is equal to 1 state, and then we said that mu, you see, this will be, let's only calculate the Z force, the Z component of the force. This will be the derivative with respect to Z of mu times B Well, we can only look at the z component of the magnetic field, let's say. Well, the z component, we have all the other components in this case. The B field is not unidirectional, but let's just ignore the other ones for the time being. They are mainly in the vertical axis. The largest component of B will also be in the vertical axis. So that will be the force mu z will be just E h bar over 2 m ml times the derivative of B with respect to z. So different values of ml will essentially feel a different force. If L is equal to 1, the possible values of ml are +1, -1, or 0. So if you just send atoms which have L is equal to 1 with arbitrary values of ml, they will, this beam of atoms will contain all values of ml practically. So some of them, the ones that have ml is equal to +1, they will bend up. The ones that have ml is equal to 0, they will go straight. And the ones that have ml is equal to -1, they will just go down. And this is what we would expect to see. And there's nothing new over here. It's just our current knowledge. What is interesting is if you do the same experiment with electrons, you send the electrons. Let's say the magnetic field is more or less downward. So the Lorentz force acting on the electron, ignored its magnetic dipole moment, will be, well, V is in that direction, magnetic field is downward. It will be V cross P is into the screen, so it will feel a force towards you. So it will, if you just send this beam of electrons, what you would expect is it should just bend towards you. But what happens is it bends towards you, but there is another effect. It splits into two. Not three, two. Which basically tells us that there's another property of the electron that we didn't know before. Well, if you compare these two experiments, this one, the magnetic dipole just causes the atom to go up or down. Here there's the electron. It again goes up or down. So it's again, it's not the Lorentz force that is causing this. It's the force due to the magnetic field. Magnetic dipole moment of the electron should be causing this. And since it splits into two, well, the magnetic dipole moment, before, if you remember, the magnetic dipole moment was proportional to the angular momentum. Now there should be some other quantity like the angular momentum. But instead of having, you see, if you look at different L values, orbital angular momentum, if L is 0, ML is 0. And 2L plus 1 is 1. So there is only one value of ML. If L is equal to 1, ML can be 0 or plus minus 1. 2L plus 1 is 3, and we have 3 possible values of ML. So the atom basically splits into 3. If L were equal to 2, ML is equal to 0, plus minus 1, plus minus 2. 2L plus 1 is 5. 5 different values of ML. So depending on what is the value of ML, the atom will either go up or upper or down, more down. But the possible values of ML is never 2. Now here we have a weird situation where the splits, there are only 2 states, 2 different states of the electron. And those 2 states are what we call spin. And well, since we have 2 states, we will assign the spin 2s plus 1 should be equal to 2, or s is equal to 1/2.
Elektron bin ikiye bölünüyor ya aşağı.
Yeah, I mean, you see, I'm sending in electrons in that direction where there is a non-uniform magnetic field. Some of those electrons, well, due to the magnetic field, they also bend, but let's forget that for the time being. Some of those electrons, after passing this non-uniform magnetic field, they go down. Some of them go up, and none of them go in between. You see, if the electron itself has some kind of a magnetic dipole moment, classically what you would expect, well, it's a vector quantity, so it should be oriented in whichever direction. So it will be oriented randomly. So there will be electrons with magnetic dipole moments in arbitrary directions. And depending on their orientation, some of them will deflect more, some of them will deflect less, some of them even less. So you will get all this spectrum. It will broaden up, but it will there will be an electron going in every direction. But what turns out is the electrons either go up or go down. No electron goes straight, no electron goes anywhere in between. So this is a new property of the electron.
If you put second magnet and split it in front of the split electrons, what happens?
Well, you have all these fantasies which you will study in 300 course. Let's say rather than drawing all these magnets, let me just draw just a rectangle. You send the electron beam. It splits. Let's say this is a magnet aligned in the z direction. Some of them go up, some of them go down. So this is what I will use to denote the magnets. Let's say you send them to another magnet, non-uniform magnet. Let's say this time it is in the x direction. Again, some of them go up, some of them go down. And then you take it through another magnet in the z direction. Some of them go up, some of them go down. Nothing fancy over here. Let's do a similar setup. You take one Stern-Gerlach experiment. It will split into two, but you block one of them. You only take the ones that go down. And then you just send it to another Stern-Gerlach experiment. Again, it will just go down. There won't be any up component. It doesn't split into two. Let's take this one. Similar setup. You block the one that goes top on the top. Then you take the Stern-Gerlach experiment aligned in along the x direction. This again splits into two. You block one of them. And then you send it through the third Stern-Gerlach experiment. It splits into two. No, it did not. In the second one, it will not. Now, we already know an example like this in optics. Have you studied polarization of light? In 2017? No, optics and waves. No, oscillations and waves. No, optics and waves. You see, there what you have a light polarized, let's say, in the z-axis. Unpolarized light. You take the unpolarized light. You put a polarizer filter, which picks up polarization in the z-axis. essential, let's just imagine this as not as a filter, but a splitter. It splits one polarization and the other polarization. One polarization goes in one direction, the other polarization goes in the other direction, if you like. Well, whichever one you like, I don't really care. Let's just say you have unpolarized light. You pick a filter. Let's say it filters light polarized along the z-axis, some z-axis that you choose. And then if you choose another polarizer, you send the light through another polarizer, which chooses again the z-axis, then it just goes straight through. Right? So if you have one, intensity is 1. After the Z polarizer, the intensity is half. Now half. Now let me discuss this one and then we will go back. Okay. And then let's say you take again the same polarizer filter. Let's say you put over here a polarizer filter in the x-axis. The intensity will be 1/2 over here and 1/4 over here. No, sorry, 0. It's 0 over here. None of it goes through. Now, let's do the third experiment. Z. Only half of it goes through. But here you put a polarizer which picks up polarization in the, let's say, z hat plus x hat direction. So half of it will go through. The intensity will be 1/4. Then you put this x polarizer. The intensity will be 1.8, 1 over 8. Basically, the same phenomena is happening over there. If you write the waves over here, you see here we have the polarization vector, which is in the z hat direction. Now, initially, there is a mixture. This picks up the ones which has a polarization vector in the z hat direction, and all of it goes through. So here we have the polarization vector in this step in the z hat direction. This one chooses the component of the light which has a polarization vector in the x direction. Well, nothing. Now let's come over here. Here at this point the polarization vector is z hat, which can be written as 1/2 z hat plus x hat plus 1/2 z hat minus x hat. So what happens is this just picks up this component. But now this component also has a x component. So that is what passes through. No. You see, here, this is 1/2. But this filter just allows all the light that is polarized in the z-axis to pass through. All the light is already polarized in the z-axis, so it passes through. Here, this polarizes only allows light to pass through if it is polarized in the x direction. But they are all polarized in the z direction. They are perpendicular. In the last one, in this one, all of them are polarized in the z direction. But that polarization can also be written in this form. And this polarizer filter just lets this one to pass through. In a sense, this polarization splits into two, and this filter blocks one of them. More or less like these ones. Similar to, not exactly. The mathematical picture, mathematical representation of this process is in fact identical to that one. We will not go into too much detail of that. Sure, sure. You see, when I say Z, it is such a system which has a magnetic field in the Z magnetic field along the Z-axis, a non-uniform magnetic field along the Z-axis. When I say X, it is a system which has a non-uniform magnetic field along the X-axis. No, I'm not looking at from the top. I'm just lazy to draw this picture. Whenever you see a rectangle, put this picture over there. Anyway, I mean, these things you will discuss in more detail in 300. But what will be important for us is now there's another quantity called spin. And spin is very similar to angular momentum. And in fact, it is why it is called the spin angular momentum sometimes. The other one is the orbital angular momentum. This one is the spin angular momentum. And, well, just like L can take values, L squared can take values h squared L plus 1, S squared can take values h bar squared S plus 1. And for electron, S is equal to 1/2. Sometimes people try to explain the spin in terms of rotation. You say spin as the term, you have probably seen it also in your first year. The Earth has a spin also because it is rotating around itself. But you see, that kind of rotation, quantum mechanics tells us that that kind of physical rotation can only take the values h bar squared L plus 1 with L integer. L can never be 1/2. Well, this is one thing against interpreting this spin of the electron as if it's a sphere rotating around itself. It doesn't work. Mainly because that kind of rotation can only take these values, not S is equal to 1/2. It's not possible. Another argument against that interpretation is we know that we have some upper limits on the size of the electron. Now, if the limit is, I think, the 10 to the power minus 18 meters, if the electron has any radius, then its radius has to be less than 10 to the power minus 18 meters. And if you just imagine the rotation of a sphere of radius 10 to the power minus 18 meters of the mass of the electron is causing this spin, then the surface of the electron should move faster than the speed of light, which cannot be. So that's another argument against interpreting the spin as a rotating sphere. For various reasons, it just doesn't work. It is an intrinsic property of the electron. It's not caused due to the motion of the internal constituents of the electron. It's just an intrinsic property, just like the mass of the electron.
Are there any particles that have spin?
Well, let's say, are there any particles that don't have any spin? Finally, we found one, Higgs. All the fundamental particles that we know have spin, except on the Higgs boson. That's the only part. The electrons have spin, the quarks have spin, the photon has spin 1. The quarks, electrons, muons, neutrinos, they all have spin 1/2, just like the electron.
Spin olmamasına diyelim. Yani bir particle varsa spin olmayan, bu bizden farklı özelliği mi spin olan?
Well, you see, as I said, spin is just like the mass. It's an intrinsic property. For example, how do we measure the spin? You see, this is a measurement of the spin of the electron. You just send a beam of electrons, not prepared in a particular way, send it through a non-uniform magnetic field, and look at how many ways it splits, how many rays comes out. If it comes out, I don't know, if you know the number of such rays at the end, then you can determine its spin. The way it interacts with other particles will be different. Like here, This is actually a system where you are looking at how the electron interacts with the photons in the magnetic field. And depending on their interaction, the electron, when it comes out, it will behave differently. So just like when you are describing a particle, so you talk about its mass, for example. No matter what you do to the particle, its mass is fixed. It's an intrinsic property of the particle. Spin is just like that. It's an intrinsic property of the particle.
Spin dönmesi oluyor değil mi?
Well, you see, the word spin, the English meaning is that something that rotates around itself. But this spin of the electron is not created due to the rotation of the electron around itself. Electron is a point, as far as we know. It's not rotating around itself. A point cannot rotate around itself. But still, it has this property called the spin, and we can measure it.
S'in bir dönüş olması ne anlama geliyor yani? Başka değerleri var mı?
Well, the S, in fact, can take values. S can be 0, 1/2, 1, 3/2, 2, etc. L can take only integer values, whereas S can take integer and half integer values. You see, essentially what this tells us is that, you see, the photon, if you consider the photon is an electromagnetic field. And being an electromagnetic field, it has a direction. So we describe the photon as a vector. A vector is a quantity that has spin 1. This observation tells us that the electron also has a spin, has a direction, sorry. Even if it's not moving, it has a characteristic direction, just like the photon. But this direction is kind of weird, in the sense that if you take a photon and rotate its polarization vector by 360 degrees, you get the original photon. If you take an electron, if you rotate it by 360 degrees, you don't get the original electron. You see, it is like this. Let's just look at this one. I will rotate this bell around this axis by 360 degrees. Is there a mark over there somewhere? No. Okay. Now it rotated by 360 degrees, right? Do you agree? Okay, the bell is now in its original position, but not my arm. I will keep rotating my arm by 360 degrees more. I started here, I rotated in this sense. Now I will keep rotating, but in order to avoid breaking my arm, I will just lift it up and rotate it further. Now, this is again back to its original configuration, but so is my arm. Somehow, spin 1/2 particles or half integer spin particles feel this difference.
Spin 1 and 1/2.
Spin 1/2 and spin a half integer particles feel this difference between one full rotation and two full rotations. You see, here, in the case of L is equal to 1, we had 3 different values of ML. 1, 0, or -1. So it split it into 3 as it's going through this non-uniform magnetic field. Now here we see that if we do the same experiment, not with the atoms, but with electrons, pure electrons, nothing else, the electrons, when they pass through this non-uniform magnetic field, they split into not 3, but just 2. Photons are not affected by magnetic field. So before I forget, so here we say that there is an ms quantum number also, which take values either plus 1/2 or minus 1/2. Yes, now your question. You mean when s is equal to 1, if we have a particle that has s is equal to 1, and if we send it through such a non-uniform magnetic field, it will split into 3. Just looking at in how many ways it separates, we cannot tell the difference. But there will be other ways of telling the difference. Now, before, we had looked at the magnetic dipole moment. And the magnetic dipole moment of the orbiting electron turned out to be E over 2m L. This is due to the orbital motion. Now, due to the spin, it also has a magnetic dipole moment. And this magnetic dipole moment essentially has more or less the same form. Let me put some G over there. Yeah. And for the spin, G turns out to be 2. So this is one way of measuring the difference. Determine the G value. For angular momentum, it is 1. For spin, it is 2. So if you can measure the gyromagnetic ratio for a particle that has s is equal to 1, you can distinguish whether it is a spin quantum number or an orbital angular momentum. Well, let's see. Let's go back to the origin of this force. So essentially, we have this deviation due to the force acting on the electron. But the force acting on the electron will be proportional to the derivative of B. If B is uniform, its derivative is 0, so there won't be any force. The only effect will be if it's an atom, you will see the Zeeman effect.
Is it atom spinning or not?
What do you mean by atom spinning?
In the first picture you talked.
You see, in that picture, well, I kind of oversimplified the problem. I just take L is equal to 1, ignore the spin. In that problem, I ignore the spin. And since L is equal to 1, the electron has an angular momentum around the nucleus, so it will split up. Of course, in practice, if you do this experiment, well, the spin will also come into the game. Due to the spin of the electron and the spin of the nucleus, there will be additional forces. Those are all ignored. So if you actually do this experiment, it will be quite a complicated outcome. At least this is what we would have expected without the spin. If you see anything other than that, then it also tells us that there's something else that we have ignored in this picture. So any other questions? Now, the spin also allows us to classify these particles. So there are those particles whose spin is 1/2, 3/2, 5/2, etc. And those particles whose spins are integers, 0, 1, 2, 3. They're also given names. If the spin is half integer, they are called fermions. And if the spin is an integer, they are called bosons. So this is essentially why we call the Higgs a boson. Its spin is 0, so it's a boson. The electron, its spin is 1/2, it is a fermion. The photon, it has spin 1. It is a boson. The hydrogen atom in its ground state, well, there is the proton, which has spin 1/2, which is a fermion. There is the electron, which is spin 1/2, which is another fermion. And if you add their spin, you get an object whose spin is either 0 or 1. That we will study later on, adding these angular momentum. So its spin, whether its spin is 0 or 1, it is a boson. The hydrogen atom is a boson. Yes?
I'm confused about the spin of photon. Does he get affected by magnetic fields?
You see, let's go back. The force, you see, there are many factors over here on this force. If you look at this force expression, first of all, it has to have there has to be a non-uniform magnetic field so that this derivative is non-zero. Secondly, ML should be non-zero. If ML is equal to 0, there won't be any force. Third, the charge of the particle should be non-zero. If the charge is 0, so the force will be 0.
So how did we find out the spin of that?
Spin of the photon.
Without that experiment?
Well, you see, this is not the only experiment that we can do. This is just one experiment that we can do. How do we know the spin of the photon? Well, let's see. Let's remember the selection rules. Delta L is equal to plus or minus 1. So if a photon is emitted from the atom, the angular momentum should change by h bar. So where did that h bar go? The angular momentum is conserved. It's the photon takes it away.
When photon leaves atom, you mean?
Yeah. When the photon is emitted by the atom loses or gains an h bar of angular momentum. Since angular momentum is conserved, it should be carried by the photon. And probably, again, from your optics courses, you remember that the light can be linearly polarized or circularly polarized. Circularly polarized photon, if it is, I think it's right-handed, it can be left-handed or right-handed. They correspond to the ms is equal to +1 and ms is equal to -1 cases. The photon cannot have ms is equal to 0. Other questions? Why? So? Well, you see, as I said, the spin of the electron tells us that the electron has a direction. That is the polarization in the case of the photon. What do you mean by phase difference? It can be arbitrary. It depends on how you create it. Well, let's see. Let's say the polarization there. Let's assume you have a photon moving in the z direction. Its polarization is x hat, which can be written as x hat plus I y hat over 2 plus x hat minus I y hat over 2. It doesn't have a definite polarization, which is, let's say, 1 over square root of 2 epsilon left plus epsilon right. So a photon polarized in the x direction doesn't have any angular moment, a definite angular momentum. If you measure it, there is a 50% probability that it will be left-handed, a 50% probability that it will be right-handed. So if you measure the z component of its spin, with 50% probability, you will measure it plus h bar. With 50% probability, you will measure it minus h bar. And if it's not in the exact direction, but in some other direction, well, just do the same trick. It doesn't make any difference. You can always, whatever the polarization is, you can always write it as a superposition of left-handed and right-handed polarized photons, or superpositions of ms is equal to 1 photon and ms is equal to minus 1 photon. It will be always possible. And the coefficients will determine the probability amplitude. And if you take its absolute square, you get the probability. So now if you have an atom, and if you want to specify the state of an electron in the atom, it's not 3 quantum numbers, but 4. We have to specify n, l, ml, and ms. These 4 quantum numbers specify the state of an electron in the atom. And their ranges, n takes values 0, 1, etc. L takes values, no, n starts from 1. 2, L take values 0, 1, up to n minus 1. ML takes values 0, plus minus 1, up to plus minus L. And ms takes values plus or minus 1/2. If you know these 4 quantum numbers of an electron, then you know the state of the electron. Yes. Okay, let's give a 10-minute break, and then we will continue.